And so I will be talking about preprocessing. I can get this, take Kevin's advice to put this on the left. Okay, great. Can you hear me okay? Oh, let me do this. Very good. How's that? Okay, very good. So, preprocessing. And so, yeah, so why a lecture on preprocessing for laminar fMRI? And I think a lot of the preprocessing that we do for laminar is, essentially what we do for just generally high resolution fMRI. And we're doing this because I think that it's actually somewhat challenging. Conventional preprocessing and data analysis techniques really aren't always appropriate for these high resolution fMRI data. And as we said before, I think that a lot of our data, we're really at the edge of being able to detect the fMRI changes within layers. We typically don't have as much resolution as we would like. As I mentioned, we cannot resolve layers, usually functionally or even anatomically. And so the idea is that there's many opportunities to lose the hard-won spatial and temporal resolutions in our data if we aren't mindful of these inadvertent losses in resolution due to improper preprocessing choices. And that's what I'd like to talk about today. And so it's interesting. There was this cool study that came out in Nature, no less, a couple of years ago. So this group, they sent the same fMRI data set to 70 independent groups, asked them to all analyze the data to see how the results would compare. And as you might imagine, it's a Nature paper, there was a lot of variability in the reported results. No two groups essentially got the same results. And it was quite striking. But what really surprised me is this slide here. They said that the strongest factor that contributed to this variability of the results across groups was spatial smoothness. And that the relevant smoothness wasn't the smoothness that they applied by, filtering the data, but it was from analytical steps beyond explicit smoothing. So implicit smoothing, inadvertent smoothing, accidental smoothing that takes place during preprocessing. And so we see that, now this was with conventional data. It's even, more important for our high resolution data if we are not mindful of these inadvertent smoothings in preprocessing. So that's what I want to focus on today. Now, just to define what are the goals of fMRI data preprocessing, this is a slide I stole from Doug. Again, we generally think of preprocessing as trying to ensure that the assumptions of our analysis are met. What are our assumptions? That the time course for any given voxel comes from a single anatomical location across a time series, the data are spaced uniformly in time, and there's some priors generally about the spatial smoothness of the activation. And so now preprocessing, we'd like to think of it as distinct from analysis. Analysis, I'd like to think of as the process of separating the signal of interest from nuisance factors or noise. And so standard fMRI preprocessing steps, I think many of you are aware of these. We start with a four-dimensional data set. We perform perhaps motion correction, slice timing correction, distortion correction, spatial normalization, spatial smoothing, and we end with another 4D data set, as Tyler described this morning. Of course, it can be done in other orders, and not everything is always done. Now, in laminar, we tend to, skip, the spatial normalization, although one might argue that generating these laminar profiles and comparing profiles across individuals is a form of spatial normalization. We tend to not do spatial smoothing, or at least we do kind of anatomically informed smoothing or layer smoothing. But generally, these two steps are not performed in laminar. And so of these steps, I just want to talk about motion correction and distortion correction. Tyler talked about slice timing correction. There's not much difference between high-res and conventional. Tyler already mentioned the most interesting aspect is when we're doing 3D API, there may not be any slice timing correction needed. I just want to talk about these two, motion correction and distortion correction, which we do a little bit differently in laminar fMRI. And so here's an example. So this is just one example that I found. It's actually pretty representative. So on the left, I'm showing some raw API fMRI data, and on the right, I'm showing the same data after conventional motion correction. This is a movie, it loops a little bit, and there's a couple of features that you might see here. So just like 4 or 5 frames. We look there, right? You can see that, this reference image that's used in the corrected data actually appears to have less blurring. But also you notice if we compare that one frame to the others, I don't know if you guys can see it from the audience, but there's a weird shift of the brain, a couple of pixels, I think, to the left. And so it looks like there's some false positive motion detection. It's seeing some motion that really isn't there. Actually, the image on the left looks a lot better, right? And perhaps this is due to noise. We see this a lot. But also the default parameters used in these motion correction algorithms result in this noticeable blurring. We see this all the time. And so this is with McFlirt, I think. Now there are ways to pass McFlirt, parameters to help kind of mitigate these issues. My recommendation, use the AFNI 3D vol reg a lot. I think this is both excellent in terms of estimating the motion and correcting the motion. And so the point here is that conventional motion correction techniques like McFlirt that work fine on conventional fMRI data don't always apply to these high resolution data. So you may need to rethink your pre-processing in order to perform well on these high resolution or laminar fMRI data. And so I'm going to follow Divya's lead. I'm going to break motion correction into two steps, both motion estimation and image correction. So first, it's a couple of words about motion estimation. And Doug alluded to something similar in his lecture. There's one piece of good news here, and that is it looks like motion estimation accuracy actually improves as we go to higher resolutions. And smaller voxels, may yield more accurate motion estimation. I think this is cool. Sometimes reviewers will say, oh, with your small voxels, you're more vulnerable to motion. Like motion's a bigger issue. But actually, I think we can estimate it even better. The idea is that we have more voxels, we have more resolution, more degrees of freedom, more information with which to estimate these parameters. And just to test this out, we applied some motion, some kind of motion taken from a scan. We applied it to some 1 millimeter data, sort of downsampled it, applied it to 3 millimeter data. We saw that the motion estimation was not that great. We applied it to 2 millimeter data. Actually, the accuracy got better. We applied it to the 1 millimeter data, and the accuracy of the motion, improved quite a lot. Again, here we know what the motion is. We applied it. We can kind of confirm that these higher resolution data, may actually compensate for this motion variability, owing to, again, this high motion estimation accuracy. So I think this is, some piece of good news. This is a video, I think, Renzo, you gave this to me a long time ago. I don't know if this is up to date. I really like this example. The idea is correcting for non-rigid motion during the time series. We know that there are dynamic distortions. There's not always perfect, kind of rigid motion due to different distortions. And so what Renzo did here, I really like. He calls it local motion correction. Sometimes I like to think of it as a restricted registration. You only kind of register you only motion correct, the tissue of interest within a local mask. And one thing I want to point out, actually, Doug kind of already mentioned this, but the idea is that we're not going to apply this mask to the image. That's going to create like an edge or a feature that the motion correction algorithm is going to get confused by. Instead, we're going to apply the mask to the region in which the cost function is evaluated, similar to what Doug had said with the BBR lecture earlier today. So that's one, I think, really, helpful technique, kind of practical method to improve the motion correction accuracy. Many algorithms have flags that allow you to, or many software packages have flags to allow you to kind of restrict, the motion evaluation to a mask of interest. And now image correction. And so I just want to point out that the image correction, if we're translating images, we're rotating images, we're applying rigid transformations, it's going to require interpolation, right? So we start with an original image grid, at 1 millimeter, say. And just to make this toy example, I put in like super high kind of spatial resolution pattern, the highest possible, this kind of simple checkerboard. And let's say we have a new image grid that also happens to be at 1 millimeter. And the subject moves by 0.3 millimeters, a half or a portion of the voxel. What's going to happen? So we see for any given voxel here, if we take a voxel in the middle and we try to estimate what the image intensity is at this new location, how do we do that? We do it by looking at kind of neighboring information from the neighboring voxels. So this voxel is intersecting a white voxel, it's intersecting a black voxel, and we may use some technique to estimate what the intensity should be at that location. How do we do that? Well, with interpolation, we average the intensity in neighboring voxels. This could be a simple linear average. This could be kind of a higher order interpolation, but we're averaging this information to estimate kind of the intensity that would be at this new location. So you can see it's going to be somehow intermediate between the white voxel and black voxel. If we consider the rest of the voxels in this image, you see that there's some blurring introduced, some averaging of the intensities, as well as these boundary effects, which I'll come back to in a few moments. So again, the point here is that there's averaging, is some kind of smoothing introduced when we interpolate. It gets more interesting. So now in this case, say we have, again, case 2. In this case, I'm going to move the new image grid by exactly half a voxel and 0.5 millimeters. We see that in this kind of case, there's a lot more smoothing. Oh, thank you. Keep it. couple of seconds. It just kind of goes out for 10 seconds. It's the weirdest thing. Thanks. Yeah, so if we shift by exactly half a voxel, we see there's sort of a lot of blurring in the data. And you can kind of see where this is going. I don't mean to be too pedantic, but, and I should point out, and I'll show you some examples. If we do, this is just a toy example to make sure the concept is clear. If we use higher order interpolation, we're going to get less blurring. What happens if we actually move the image even further, right? So I showed you 0.3 millimeters, I showed you half a millimeter. Now let's move this new image grid exactly by 1 millimeter, right? We might think that we're going to get more blurring. There's more of a translation. But as Luca just indicated, yeah, I think that in this case, we actually get less blurring, right? In this sort of special case, right? So you can start to see that as we kind of translate the image, there's some like this cyclic nature. We get more blurring, less, zero, more, less. We're going to get this sort of cyclic kind of blurring induced as we move the image around. That's something that I'll show you some examples of here. Again, in this special case, no blurring due to interpolation. Okay, I don't want to get too pedantic, but you can imagine you can shift the image in two directions. You can do homework, try to figure out what the blurring looks like here. It gets even more interesting. So say we rotate the image. Again, more interesting pattern. I just want to point out here that there's some voxels, like this voxel in the center here, that are going to experience less blurring than others, and some voxels will experience more, depending on this pattern of translation and rotation. And so the averaging imposed by interpolation is going to induce a spatial blurring that's going to vary across the image. It's not always so simple. And we can see this, the resolution losses due to motion correction. This is a case where the subject was nodding their head by 2 degrees. I'm looking at, this is the additional smoothing due to this interpolation induced by the motion correction. You can see this kind of spotty pattern, both on the folded surface and on the inflated surface. And we get a different pattern if they shake their head by 2 degrees. And so the idea is that the types of motion can induce this unwanted or additional smoothing due to interpolation that reflects the pattern of motion. And so, as Divya mentioned, we also get resolution losses when we correct for B0 distortion. And so here you can see this kind of cyclic nature. Why does it look like this? Well, again, the idea is that in some locations, the voxels are being shifted by 4 millimeters, 3.5, 3 millimeters, 2.5, 2 millimeters, etc. So you can see that this map that I'm showing, this represents the additional smoothing imposed by interpolation. It kind of looks like the field map, right? If you looked at this quickly, you might think this is the phase of one of Divya's field maps, right? So the idea is that we see that these patterns of resolution losses actually reflect in many ways the pattern of distortions or the interpolation that we impose on the data. So last case, so the idea here is that now if we consider a new image grid, right? So the original data is 1 millimeter, we have a new image grid that's half a millimeter. And if we move that image grid, by the same amount, half a millimeter, as I showed you before, when I considered the new grid that was 1 millimeter, this half a millimeter shift was exactly half of the voxel. It introduced the most blurring. In this case, with this finer image grid, the exact same translation, 0.5 millimeters, will result in no blurring in this case. And so this finer grid generally results in less blurring. And so you can start to see a strategy for mitigating this blurring is to go to finer grids for your new image. And this can be seen in this example here. This is some 1 millimeter data showing again that upsampling can substantially reduce the blurring effects of interpolation. So this is the blurring induced by, I guess, motion correction in this case. So we see, kind of different blurring, again, induced by interpolation across the image. If we apply the exact same motion correction to the data after upsampling it to 0.5 millimeters, there's much less induced blurring. So you can see here, this is a really simple way to reduce the blurring in your data. Just upsample it. What's the downside? Well, more disk space, larger file sizes, some algorithms, work more slowly, but this is a really kind of practical and simple way to reduce blurring in the data. So as an aside, how are we estimating this blurring? These maps I'm showing you are pretty cool. Like, how do we do this? Well, there's a bunch of different ways. This is a method that we've used several times. So what we do is we generate a sort of synthetic time series of IID noise, zero mean, unit standard deviation, just white noise that has the same grid as the fMRI data. And we just pump that through our pre-processing, right? And then we look at the resulting temporal standard deviation of this pre-processed noise. And this temporal standard deviation, or TSDD, will be related to the level of smoothing, right? Because if there's no smoothing at all, the noise will have a standard deviation of 1, which is what we input. If there is smoothing, the noise standard deviation will be somewhat less than 1. And we can simply map out this transfer function between noise, standard deviation, and the level of smoothing. So this is kind of a fun way that you can use to evaluate the smoothing in your preprocessing streams. So of course, the spatial blurring varies across different interpolation algorithms. And this plot is a little bit confusing because it's making sort of 2 points at once. And so I've broken it down. So if we apply motion correction to our original data across different motion correction interpolation methods, sync, quintic, cubic, linear, going from higher order to lower order, we see that these lower order interpolations induce more blurring in the data. Makes sense. Now, if we first upsample those data using a nearest neighbor interpolation, so say this is the 1 millimeter data that I told you about before, so we upsample to 0.5 and perform the same motion correction, we see much less blurring in the data, just like I showed you before. Again, it starts to creep up if we use these lower order interpolation methods for the motion correction. If we upsample the data instead using a cubic interpolation, a little bit lower order, we actually start seeing some of these benefits start to go away. And if we upsample the data using a linear interpolation, what's interesting is that it's actually not much better than the original 1 millimeter data. So what this is saying is that if you are going to upsample your data, if you are going to interpolate the data before running these algorithms, just make sure to use a higher order interpolation. Very simple. Now, when we project our fMRI data onto the surfaces, the surface meshes that Doug showed us earlier, that's also a form of interpolation. And what's interesting is that, I think, who mentioned it? Maybe Doug. Oftentimes, our fMRI data are much higher resolution than our anatomical data, kind of ironic. And so what that means is that in these, if you look at the original mesh shown here in blue, oftentimes it's pretty coarse, and it's possible that at this original mesh resolution, when we project the fMRI data onto the surfaces, there's just more fMRI voxels than there are vertices. So what that means is that we're going to actually lose a lot of our fMRI voxels. And so one way to compensate for this is to simply upsample the mesh. Shown in these red vertices, if we just add more vertices to the mesh, we'll see that we're actually going to retain more unique fMRI voxels, fewer voxels are going to be missed. Also, there's less distortions as we project the fMRI data onto the surfaces. If the not a vertex nearby, if the nearest vertex is a little bit far away from that voxel, you'll see a little bit of distortion of the fMRI maps. Also, if we refine the surfaces, we can see that not only do we retain more voxels, but we see sort of less blurring. In this case, in these columnar maps, you can see that the maps are much more distinct if we project the fMRI data onto the refined surfaces. Again, this is super simple. What's the downside? More vertices, bigger files, slower processing, but it's a really simple approach to increase the resolution or accuracy of your maps. I think Doug talked about gradient nonlinearity. Maybe I'll go over this quickly. I think, Saskia mentioned it too. Again, the idea is that we typically assume in our image reconstruction that there's a linear relationship between the opposed gradient from our gradient coils in space. And oftentimes that really is violated at the edge of the object. Well, it's also violated in many sort of modern gradient coil designs. It's because, the engineers can generate a linear field if they want, but they tend to cheat it's a trade-off. By kind of rolling off, relaxing the linearity, they can achieve lower peripheral nerve stimulation, kind of faster switching. And so what happens is this induces, especially at the edge of the brain, these strong distortions. We call this like the balloon head artifact. There's a pinching around the neck. This can be corrected online, as Doug had mentioned. The good news is that this geometric distortion is the same for any object, same for any pulse sequence. It's just a fixed parameter of the gradient coil. It depends on the gradient coil winding and, of course, on the head position. If the subject moves their head, if you scan a subject Monday and scan them on Tuesday, their head is in a different position, they'll have different distortions. And again, this is an important distortion to consider when aligning data across different sessions or across different scanners, as I think Daniel also alluded, as well as Doug, I think. And so just to talk about the accuracy of this distortion estimation, we can estimate the accuracy. So typically the scanner manufacturers provide us, as Doug mentioned, these spherical harmonic coefficients that estimate the gradient nonlinearity. But do we trust them? One way in which we can validate these gradient nonlinearities is to use a phantom with known geometry, such as my favorite ball grid phantom that Anders actually built. we can see that if we apply the distortion correction to the ball grid, we know the spacing of the different fluid-filled spheres. We can evaluate the accuracy of this gradient nonlinearity distortion. Now, when we apply this distortion to the fMRI data, you can see here, so I think this is the original data off the scanner. Here's the distortion corrected. I don't know if you guys can see, the back of the brain is sort of wagging a little bit. I don't know if you can see in the back row, but this correction, because these data are so high resolution, you really see the noise in the original image, and it's much easier to see the blurring in the corrected image. And this is really unacceptable. And so, again, because it requires interpolation, blurs the image, Divya had mentioned, one simple strategy. The API data are just really delicate. You just don't want to be messing with them. You don't want to be applying warps to them. A much better method, Peter Koopmans does this a lot, just to form the anatomical data. If you're doing a surface, oops, sorry, I went too far. If you're doing a surface-based analysis, you can also just apply the distortions to the surfaces to avoid this interpolation blurring in the API data. And again, this is just a fun fact. Any geometric distortion, gradient nonlinearity distortion, B0 distortion, we think of these as kind of moving the voxels around, kind of, altering the positions of the voxels, altering the intensities of the voxels, and that's true. But if you think about it, they're also affecting the volumes of the voxels, right? So this gradient nonlinearity, as well as B0 distortion, changes the voxel size. And this is a map of how one of my favorite gradient coils actually changes the voxel size. What's interesting here is that I think that, so this is literally the change in voxel size. So red means the voxel size is bigger than what you think. This is places where the gradient is a little bit weaker than you think. But actually, it's pretty interesting. The blue voxels show you places where the voxels are smaller than what you think, right? So this is both good news and bad news. This happens to be in visual cortex. The voxels are actually a little bit smaller than the nominal voxel size. So these B0 distortions, gradient nonlinearity distortions, good news and bad news, right? It can be good, can be bad. But the point is that, and this isn't something we can correct, we think that the voxel size is the same across the brain, but it's varying due to other effects, but definitely due to these geometric distortions. And just to point out, we also see when we apply these gradient nonlinearity corrections, we also see resolution losses due to interpolation. As I said, the pattern depends on the gradient nonlinearity, which means that it changes with the gradient coil, and of course changes with head position. This is a map, again, of just the additional smoothing imparted into the data due to this interpolation. So what can you do? I think it's hard to avoid interpolating the data at all, right? We need to interpolate at some point. But the question is, how do we interpolate the data intelligently, right? And so I told you, you can upsample the data. So here's a case in which we're applying both motion correction, I think actually three, motion correction, EPI, distortion correction, and of course, anatomical registration and gradient nonlinearity distortion correction. And you can see that the additional blurring induced by interpolation, if we apply these three interpolation steps, one after the other, we see that these three consecutive resampling steps result in a pretty high degree of blurring. I guess the only good news here maybe is that it's roughly spatially uniform, but it's still pretty unacceptable. Now, what can you do? So this is a bilinear interpolation, again, quick, but low order. We can increase, to go to higher order interpolation, in this case, spline interpolation. So I think that there's still a high degree of blurring here, and maybe a little bit less, and maybe less spatially uniform, so some good, some bad. But I think a better approach, and maybe one of the few kind of best practices that we have in high resolution fMRI is to compose these transformations to do a single resampling step. This is advocated by the Human Connectome Project, an article that I was involved with a few years back. So the idea here is to mathematically compose all of the transformations to calculate one one single transformation of the data, and therefore single resampling. And so this is really advantageous. Much less blurring, but still, we're interpolating. And so these resolution losses due to interpolation are present, again, spatially non-uniform, and something that we need to, remember when we interpret our data. So again, we can apply these transformations either to the EPI data, we can apply these transformations to the anatomical data, as Divya said. Again, the EPI data are just very delicate. And so oftentimes I think it's better. So again, instead of removing the distortion from the EPI data, you kind of apply the distortion to the anatomical reference. You can do this to the MP range data like Peter Koopmans. You can do this, you can apply this to the surfaces as well, again, in order to minimize this blurring. Okay, I think that's mostly what I wanted to talk about, but I also wanted to just end by I think Anna's going to talk about this in a couple of minutes. Yes, confirmed. But I just wanted to point out again, in pre-processing, I like to think of pre-processing as ensuring that the assumptions of our analysis are met. And I think it's important, therefore, to be mindful of these assumptions, mindful of these priors. Now, what we do in laminar is pretty weird, right? We're generating these, laminar profiles generally, maybe looking at 20, 25 depths across the cortex, with voxels that are there may be only 2 or 3, voxels, unique voxels that span the cortical thickness. And you can see here, this is again from Peter Koopmans. If he made the profile through this green line, we see this kind of stair-steppy kind of profile of intensities. If he makes a profile through the red line, again, it gets a kind of stair-steppy kind of profile of intensities. If he averages many, 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 many lines, again, the stairs, like the transitions between the voxels are at different locations. And if he averages these together, he gets kind of a smooth profile like we're accustomed to seeing. But the point is that what we're doing in this analysis, again, the larger the ROI, the less kind of stair-steppy the profile is, but it assumes that all voxels within this ROI have similar activation or intensity across layers. And we just need to be mindful of this assumption. We need to be thinking about how big the ROI is. And of course, we typically look at these, one-dimensional profiles. It's a form of smoothing. We also perform anatomically informed kind of layer smoothing, which I think is more often applied when we're looking at these sort of 2D or 3D maps of the layer profiles. We don't need to perform laminar smoothing if we're going to generate these profiles. But if we want to look at these 2D maps like Renzo does, or 3D maps, we again impose, this layer smoothing, which is kind of, again, instantiation of our prior. We think that the activation within these layers is the same, which is why we can perform the smoothing. If that's incorrect, then that's going to introduce bias. And one last plug before I wrap up, and that is, so smoothing the data is okay, but I think it's important to look at the unsmoothed data. I think of it in terms of, if you're looking at a scatter plot of a bunch of noisy points, you want to see the trend. Great, fit like a polynomial, fit aligned to those noisy points to try to understand the trend. You would never just show the line without showing the noisy points underneath. And so I think it's really important, if you are going to smooth the data, to look at before and after smoothing to make sure that the smoothing isn't imposing any features in the data that aren't present in the unsmoothed case. And again, I think Anna's going to talk about this more today, I think, right? Tomorrow. Oh, sorry. Okay. Anna's lecture tomorrow. All right, cool. Thanks. All right, let me wrap up. Again, very simple lecture. Interpolation is really unavoidable. We have to interpolate our data at some point, and it introduces spatially varying resolution losses. I think that, again, this one-step resampling minimizes the interpolation. I like FSL's convert warp and apply warp tools for this. They're really nice. Also, upsampling the data, including upsampling the image grid, upsampling the surface mesh, helps to limit the effects. They're not going to go away, but it's a really simple way to do this. I think that Valentin Kemper, right, Renzo, I think he used to upsample his data like right off the scanner. I think this is actually doing it on the scanner is a nice way of doing it. Anyway, we can talk about how to implement this later. Yeah, conventional preprocessing tools underperform. They're made for conventional data. And so I think it's fair, but we just need to be mindful of this. I like AFNI. Again, you can get McFlirt to work with the proper flags. One tip, as I mentioned, just running this, spatiotemporally white noise through your pipeline and sort of examining how much blurring you're imposing, I think is a good idea. And it's pretty simple. Again, this resulting temporal standard deviation provides you with some measure of your smoothing. And so I think this is a really simple approach. Geometric distortions, again, often not really thought about, both B0 distortions, gradient nonlinearity distortions, induce unavoidable spatially varying voxel sizes during the acquisition. Can be good news or bad news. Bigger voxels, smaller voxels, depending on the sign of the distortion. Now, what I haven't discussed, of course, is even smarter removal of noise, right? I mean, smoothing is one way to remove noise, to impose a prior. Luca's going to talk about how we can more intelligently remove thermal noise, which I'm looking forward to. I think Jingwen is going to talk about addressing physiological noise. Oh, okay. Looking forward to this as well. Again, the structured noises, can be harder to address in these data. Okay, so I'll stop. Just want to thank Anna, Olivia, who did all those compositions, Renzo for the cool movie, Doug for the slides, and Jianbao for the work on the motion correction. And yeah, thanks for your attention. And so, yeah, happy to take any questions. Again, simple stuff, but pretty important. All right, thanks.